All right, and we're continuing on with Chapter 6a. We're now in Part 2, starting with question number 5. Number 5 says, basically 5 has a theme as well, so it's a half value layer thickness, or HVL. And Part A just says, I need more help with this. So let's just kind of talk about what the half value layer thickness is. And just to speak about it in really broad terms, if we have an area, we want to know how far halfway is, basically. And this kind of reminds me of the riddle, how far can you run into a forest? We can run halfway, because then you're running out of the forest after that. And so we kind of see a similar thing with sound. If I've got, this much energy in a sound beam, how far can it travel before it attenuates and is half as much as it was? And so that's what we're looking for. When does 3 decibels of attenuation occur? At what depth? Because we know that a negative 3 decibels is going to equal a beam that is half as strong. So at what depth do we get to negative 3 decibel change so we know that our beam is now half as strong? So we can think of a couple other examples of how half value layer thickness might apply to other objects. Another example that I sometimes use is a book. The half value layer thickness of this book depends on how many pages are in it. And halfway through the book is the half of the number of the pages. And so this book has 584 pages in it. So that would mean page 292 is the halfway point. So we could say the half value layer thickness of this book is 292 pages. So this is at what point the sound beam would have attenuated by 3 decibels, is getting through that thickness, the 292 pages, if we wanted to apply it back to ultrasound beams, and this was soft tissue. So I hope that kind of helps understand all we're looking for is a depth or a value at which we're getting to that negative 3 decibels of attenuation. All right, and then question 5b, which also has a subpart 1, says, why do we need to know the half value layer thickness and how is it applicable? To be honest, I wouldn't spend a ton of time on HVL. You might have a question on it, if even that, on your boards. Really what the idea is that if if negative 3 decibels of attenuation means that the power is half gone, at this point in time, our beam is now half as strong as it was, and any reflectors coming back from here are actually going to attenuate again by half. And now we only have a quarter of the power left of our beam. So we kind of want to make sure that we are getting far enough into the body to get meaningful echoes from multiple places, because it's going to attenuate on the way back as well. And if we just don't have strong enough echoes coming back, then we can't do anything with them. And so that half value layer thickness is more of a verification that we're getting far enough into the body with enough power and have enough power for those echoes to come back. We actually see this a lot more in X-ray. They need to make sure when X-rays are going to be half as strong as they are, so they know how much lead to put in the walls and that kind of stuff, and where it's safe to be around that room that has the X-ray in it again. So it's not that it's not applicable to ultrasound, it's just not applicable to the everyday scanner's operation. So let's just take a look at a quick math example just to talk about it in math terms. So here I've got a column with centimeters marked down the side of it. And the half value layer thickness is going to be very dependent on the attenuation coefficient. The attenuation coefficient tells us how much attenuation occurs per centimeter of travel. So if our attenuation coefficient will start with 1 decibel per centimeter, that means that for every centimeter that this sound wave travels, 1 decibel is going to attenuate out of it. And again, we're looking at what point do we get to negative 3. So if we're working with 1, we've got 1 decibel gone. At 2 centimeters, we have 2 decibels gone, and at 3 centimeters, we have 3 decibels gone. So with a sound wave that has an attenuation coefficient of 1 decibel per centimeter, the half value layer thickness is going to equal 3 centimeters. Let's try another one. AC coefficient is, we'll say 0.5 decibels per centimeter. And now we want to know what the half value layer thickness is. When are we going to get to -3 decibels? So at 1 centimeter, we are 0.5 decibels. 2 centimeters, we're at 1 decibel. 3 centimeters, we're at 2.5 decibels. At 4, we're at 2 decibels. 5 centimeters in, we're at 2.5 decibels of attenuation. And at 6 centimeters, we get to 3 decibels of attenuation. So for a beam that has an attenuation coefficient of 0.5 decibels per centimeter, the half value layer thickness is 6 centimeters. So essentially, it is 3 decibels divided by the attenuation coefficient. So for this green one, at 6 centimeters, the beam is now half as strong as what it was. And that would tell us any reflections coming back from 6 are also going to be actually a quarter strong as they were when they get back. So again, it's just another way to make sure that we have enough energy going in to a reasonable depth and that we're going to get meaningful echoes back, and a way to check it. Moving on to question number 6, we've got a theme for this one too. It is the attenuation coefficient. And 6a here says, what is the purpose of the attenuation coefficient? And then we have a 6a part 1. What factors influence the attenuation coefficient in ultrasound imaging, and how does it affect the quality of the ultrasound image? So let's look at the core question of 6a first. What is the purpose of the attenuation coefficient? The attenuation coefficient really just tells us how much attenuation will occur over the travel depth of a sound beam. So it really just is a way to recognize how much power is leaving the sound beam, and I guess that really just kind of informs how the image is going to appear. If we have a higher frequency transducer, we know that that is going to attenuate much faster because attenuation and frequency are directly related. And then we know that distance and attenuation are also directly related. So if frequency increases and distance traveled increases, then we just know that we're going to have less attenuation. And really what a lot of the physics that we're learning about, the goal of it is to inform your decisions then as a clinical sonographer. So if you know you need to image 20 centimeters into the chest or into the abdomen, you're not going to choose a 15 megahertz transducer. You're not going to have enough penetration because of attenuation. That's not going to work for your imaging. So a lot of the physics that we're learning is to better inform you of the limitations of ultrasound so you can make appropriate decisions clinically. Part I then says, what factors influence the attenuation coefficient in ultrasound imaging, and how does it affect the quality of the ultrasound image? Basically just kind of talked about it. The attenuation coefficient is going to be related to distance traveled and has a lot to do with the frequency. We see that there are a couple formulas that go with attenuation coefficient. The first one being that attenuation coefficient equals the frequency divided by 2. And then we also have that the attenuation coefficient equals 0.5 decibels per centimeter per megahertz. And so this, again, also helps to recognize that increasing the distance and increasing the frequency will increase that attenuation coefficient. As far as it affecting the quality of the ultrasound image, already kind of addressed that as well with the idea that we need to choose the correct transducer frequency to image far enough into the body for what our goals are. All right, and then 6b says, can you clarify the second formula for attenuation coefficients? We've got attenuation coefficient equals 0.5 decibels per centimeter per megahertz. And I believe it's just explaining that the attenuation coefficient is always 1/2 the frequency. Is that right? And yes, essentially that is what it's saying. The other attenuation coefficient formula that we had was frequency divided by 2. And it's important to remember that both of these are soft tissue attenuation coefficients. They are only going to apply to ultrasound in soft tissue. The formula, though, that you particularly asked about is just basically saying that the attenuation coefficient will decrease by 0.5 decibel per centimeter per megahertz that is being used. So yes, if we're going to use an 8 megahertz transducer, we will see 4 decibels of attenuation per centimeter. And then to figure out the total attenuation for this, we could really just do 0.5 decibels multiplied by the distance. So we could just say 8 centimeters again, multiplied by the megahertz that's being used. And we are on to question number 7. And 7 says, how can an increase in frequency cause an increase or decrease in scattering, attenuation, and absorption? And then there's a 7a that says, how is there more absorption and scattering despite also more attenuation? All right, so we know that attenuation is going to be directly related to frequency. And we saw that with the attenuation coefficient, frequency divided by 2. Attenuation and frequency are on the same line, so if frequency increases, then our attenuation coefficient increases, which affects the total attenuation, because total attenuation is going to be the attenuation coefficient multiplied by the distance. So then we see if attenuation coefficient increases, total attenuation increases, and if distance increases, then total attenuation also increases. So frequency, attenuation coefficient, and distance traveled all affect the total attenuation. So that's just informed by our formulas, and I think we've talked about it in some of the other ones as to why, mostly because of how those really high frequency sound beams kind of bounce around all the particles and kind of makes everything vibrate a whole bunch more. It just loses power out of the system a lot quicker. But part A then says, how is there more absorption and scattering despite also more attenuation? And that one is kind of like an order of process. The concept of attenuation is due to absorption, it's due to scattering, it's due to reflections. So, if this is all of our ultrasound power coming in to the sound, and it's going to interact with this interface here. At this interface, we can have one of 3 things happen, or actually one of 4 things happen. We can have a reflection where sound is sent back. That'd be our reflection. We can have a scattering where sound is sent into different directions. Or we can have this interface absorb a bunch of our sound energy. And then the last thing that can happen is that sound will propagate through. And typically at that interface, if sound propagates through, something else has happened and we're only getting a fraction of our sound continuing forward to go to the next interface. The whole reason that we get our ultrasound pictures, though, is because there's a reflection or because there's scattering. Absorption is going to result in kind of a loss of power, which typically results in a loss of echoes. We see that a lot behind bones and things that cause shadowing in our images. And so scattering, reflection, absorption all cause attenuation. And the attenuation is just the weakening of the sound beam. So these 3 things weaken the sound beam, which is that attenuation. All right, and our last question for Chapter 6A, Part 2, question number 8. Why does absorption happen at opposite densities rather than just highly dense structures? Unfortunately, your question is missing a little context for me, so I don't know that I can answer this exactly how you intended because there are some incorrect assumptions happening in your question. So let's just talk a little bit more about absorption in general and maybe what I'm kind of thinking you're leaning towards, maybe confusing the impedance in there a little bit, so which actually is all kind of related to one another. So let's talk about a few things with absorption and reflection and all of that. So absorption occurs when you actually have really low density items. Remember, bone is one of our big absorbers, right? And bone we consider to not be very dense. There's actually a lot of space in bone. And so it's actually not very dense, but it is very stiff. So bone has increased stiffness, but decreased density. And the decrease in density is why bone is actually a pretty good absorber. Think about acoustic panels in like a recording studio. Usually those are made of foam, and foam has a ton of like little air pockets and stuff in there, right? And so as the sound goes into this foam, it kind of gets trapped in those pockets of space and can't get out. And so that's the absorption part of it. The foam takes in that sound and doesn't let it back out. That's the whole purpose of it. And that's kind of what bone ends up doing too. So it's actually less dense the object is. It's actually going to absorb more of the sound. We see that with air even. Air compared to water. I think air absorbs a lot more sound than water would. And so the density of the material will affect the absorption, but it actually is lower dense structures absorb more sound. When you have a really highly dense structure, that's actually going to reflect more sound. So if we had a really solid structure here and sound came into it, it's going to more likely reflect that sound. And we see that like with the diaphragm. The diaphragm is a very fibrous structure. It's a high reflector and it reflects quite a bit of sound back to the transducer. And so high dense objects reflect more sound, low dense objects are going to absorb more sound. Both cause attenuation though. And the other thing that we see with high density is increased impedance. So if you recall impedance, the formula for that impedance is going to be density multiplied by the propagation speed. So if density increases, impedance increases. And impedance again means resistance to sound traveling through it, which is why increased density is going to reflect more. The decreased density of the bone is going to mean that more is absorbed into it. So it allows sound into it, but it doesn't really allow sound to escape it. So I hope that maybe answers your question a little bit. I apologize that I couldn't answer exactly because it's just, again, making some wrong assumptions in there. But the level of density will affect the absorption and the reflection that occurs. The only other thing I was kind of thinking with your question is that in part 6b, we do talk about there needing to be a difference of impedances when we are talking about sound coming in and reflection occurring. And so there does need to be a difference. These cannot be the same impedances if reflection is going to occur, especially with normal incidents. So maybe that was a little bit of it as well, but that's going to be covered a lot more in part or chapter 6b in the next video.